Okay, a couple of things. Let's see. Scheduled for today is titration experiment, and scheduled on Wednesday also a titration experiment. Um, so I think what we're going to do today is we're going to continue lecturing because we're almost like right to titrations and sort of solution stoichiometry. So I think we're going to do today, just sort of schedule wise, give everybody a heads up. I think today we will lecture here, and on Wednesday we will actually do experiment 21. I think so. On Wednesday we'll do the one that's scheduled for today, experiment 21. Monday, we will do experiment 22, which was originally scheduled for Wednesday. And on Monday, originally, our next exam was, so that's going to be moved to the following Monday, um, which at that point, I'm not sure what date that is. That's December, believe it or not. I almost want to say 7th. Does that sound about right? Let me see here. Let's see here. I think it would then be, we're there. And so I think it is the 7th will be the final, not the final exam, 4 will be on that day. Um, so let's see. Yeah. So I think that's sort of the game plan. Yeah, you could turn it in, just get it all in. It's fine. Um, so that's sort of the game plan because again, the fourth exam is going to cover chapter 16 as well. So we're almost done with 15, and then we have 16 to go. So obviously, I don't anticipate we would finish perhaps by this Wednesday. So that's sort of the game plan. So we'll move 21 to Wednesday. We'll move 22, which was originally on Wednesday to Monday. We'll move the exam, which was originally next Monday, to the following Monday. And then at that point, we're almost at the end, I think. So then the following Wednesday after that is the final, I think. So that's whatever day that is there, the 14th, 15th, 16th, perhaps, something like that. Any questions on sort of schedule wise, what's going on? Yeah. Okay. And again, exam 4 will cover chapter 15 and 16. So hopefully we'll be done with 15 today, and then we'll get a good chunk of it 16 out, hopefully as well on Wednesday and stuff. So that should be good. That'll give you a week, hopefully, to kind of study all that stuff. Any questions on any of that? There will be. So for the final, I'm trying to think. There will be for probably. I think there'll be some stuff for the final, especially from the last chapter, which is 17, I think. So there'll be some review stuff for that chapter, I think. For the rest of the chapters, you could probably use the previous stuff. I'm trying to remember if I have something specific, for the final or not. But it will be comprehensive since we're talking a little bit about it, and it will cover everything. Obviously, we covered the entire semester, all I guess 17 chapters. That would be. Yeah. Okay. Any other questions on any of that? All right, then let's continue on. So we kind of finished talking there about molarity. We did all kinds of different molarity type problems, molarity involving obviously the entire compound, molarity involving ions as well. So the next very common sort of process that involves solutions is what is known as dilution. And in a dilution, what we essentially do a lot of times is we take a stock solution, and a stock solution essentially just means that it's usually a very concentrated solution. So it has a very high molarity. So usually when you have that stock solution, the molarity is relatively large. And typically what we do is we usually want to use it in a more dilute fashion. So usually the process of a dilution is a lot of times we just add water. You don't always necessarily add water, but a lot of times you do because water is a very common solvent. So it's added a lot and used a lot as a solvent. But technically, water doesn't have to be the solvent. But when you do a dilution, you typically add more solvent. So a lot of times people do say water because of that. And again, as I sort of mentioned a little bit earlier today, the reason the molarity goes down is when we add just say water, we're really increasing the bottom number here in this sort of calculation. So the bottom number gets larger, which means when we do the division, we end up with a smaller molarity. So the molarity goes down as we do a dilution. And that's because the moles here pretty much remain the same. So in the process of a dilution, we don't do anything with sort of the moles. We just really add more solvent. More solvent increases the total volume of the solution. Increasing the volume of the solution brings the molarity down um, in that particular solution. Higher the M or molarity number, the more concentrated it is, the lower the molarity number, the less concentrated it is. So there is a dilution equation that's oftentimes used, and that is M1V1 equals M2V2. And this is what is sometimes referred to as the dilution equation. M1 is molarity, V1 is volume. So this is usually before on this side, the dilution as it says. And M2 is molarity, V2 is volume. This is usually after. Now, you will sometimes see a more generic version of the dilution equation, which is sometimes people use C1V1 equals C2V2. And the only real difference here is C just means concentration. So first concentration, second concentration. And what it really means is we don't necessarily always have to use molarity. We could use something like what we saw, percent mass, percent mass to volume, etc., percent volume to volume. But since molarity really is sort of the most common unit of concentration, oftentimes most people refer to it as M1V1 equals M2V2. Now, we also talked about earlier that when you use molarity, you typically want to use the volume in liters, which is moles divided by liters. That's because the liters will cancel and you'll end up with moles. This is one of the few sort of formulas that if you want to leave the volume in milliliters, as long as it's milliliters on both sides, it's okay. So you could actually leave the volume here in milliliters. And the reason why it works out in this formula is, let's just say we were solving for M2. M2 would be M1 V1 divided by V2. And as I mentioned earlier, if you take milliliters times molarity, you actually get what is known as millimoles. And that is because molarity is most often thought of as moles per liter. It could also be thought of what is known as millimoles per milliliter. And they're basically the same thing because the milli here and the milli here cancels, and you end up with moles per liter. So really when we do this calculation, if we just look at units, we are taking millimoles over milliliters. And if we times it by milliliters and then divide by milliliters, milliliters will cancel, which essentially gives us millimoles divided by milliliters. Millis cancel, gives you moles per liter. That is a long explanation to tell you that if you use this dilution equation, if you want, you can leave the volume in milliliters if you're multiplying by molarity. If you want, you could also convert it to liters and do it that way as well. So sometimes it'll save you some time if you kind of leave it in milliliters, because a lot of times when we look for volumes of stuff, the units are very commonly milliliters is what we're looking for. So this is one case where it is okay to leave the volume in milliliters if you're multiplying by the molarity. Again, you can also convert it to liters if you want. So either one is perfectly fine. So you can use liters on both sides. Now, I don't want you to be confused. If you slowly have a problem like what we did earlier, where you just have volume and molarity, you definitely need to convert it to liters. So if it's not a dilution problem, you do need to convert those volume into liters. Otherwise, you will get the wrong answer. So that's really important to make sure that you keep that in mind. Any questions on that? Okay. So sort of the steps to a dilution is kind of similar to, let's come back, to making a regular solution. So usually what we do is we usually will have a bottle that is more concentrated. So let's just say we had a 19 molar solution and we wanted to make a 2 molar solution. So when we use this formula M1 V1 equals M2 V2, and perhaps we solve for V1, what usually that V1 means is that's the volume of the more concentrated solution. So just to say we calculated it and it was, 2 milliliters or something. That means that we would take out 2 milliliters of this first guy, and then we would fill the rest with water at that point, basically to make our solution. So whatever our final volume was, we'll go with 100 milliliters. We'd fill the rest with water and basically give it a mix. So a lot of times you can use a volumetric flask to do that. You take a little bit of the concentrated solution, which is what they have in here, a little bit of water in there, add it, and then add the rest with water to the line, give it a mix, and it's going to basically give you a more dilute solution. So dilution is really, kind of like we talked about, you got like a drink that's full of ice, you kind of leave it in there, tastes really good, when you get it, but you come back maybe an hour or so later, all the ice is melted, and obviously all that water has added to that solution, and it's going to make it obviously not taste as strong and can be a lot more dilute because it's basically watered down. Any questions on that? Okay. So why don't you give this a go? What is the minimum volume of 2 molar sodium hydroxide that is needed to make 150 milliliters of a zero 0.8 molar sodium hydroxide solution? Should take a minute or so and see what you come up with. Okay, so this is a dilution problem. So just visually, what we got going on here is we have a bottle of basically 2 molar sodium hydroxide. We want to take a certain volume of that out, and we want to make a new solution that has a total volume of 150 milliliters and has a concentration of zero 0.8 molar. So no reaction happening here. It's just sodium hydroxide and sodium hydroxide. So this is just a dilution. So M1V1 equals M2V2. Typically speaking, M1 and V1 are the more concentrated solutions. They don't necessarily have to be, but usually that's what people sort of label them. So our M1 here would be 2 molar. Our V1 is what we're looking for. Our M2, which is the more dilute solution, zero 0.8 molar, and our V2 is 150 milliliters. So basically here we will be solving for V1. V1 would equal M2 V2 divided by M1. Again, in this case, if you want, you can convert the volume into liters, or you can leave it in milliliters in this case. So I'm going to leave it in milliliters. So this can be 2 molar times my 150 milliliters divided by 0.8 molar. Again, the molarity and molarity cancel, leaves me with milliliters. If you convert it to liters, you would have 0.15, and the only difference is your volume would be in liters when you solve for it, which is perfectly fine as well. So if we do that, you will end up with 2 times 150 divided by zero point 0.8. Oops. Try it again. 2 times 150 divided by 0.8 there gives me 375. That doesn't seem right. Let's see here. I write a number wrong here.
You ended up flipping the 0.8 and the 2.0 molars for.
Thank you very much. I'm like, that didn't seem right there. It's a good thing they invented erasers. Let me try that again. All right. All right, take two. So point it up on top. Seems good. Try that. And 150. There you go. Divided by 2 molar. Molar cancels. Now let's see if we get a better number there. All right, 150 divided by 2 gives me 60 milliliters. Cool. Thank you. So that 60 milliliters, just so we're clear, what that represents is it is 60 milliliters of basically the more concentrated sodium hydroxide solution. So if we were to make this solution, we basically would go to our more concentrated guy and we would take out and throw in here 60 milliliters of it, basically. Now, the question is my volume here is 150. Should I add 150 milliliters of water? And the answer should be no, you should not do that. Because if you added 150 milliliters of water, you would have 150 plus 60. And that's going to give you a total volume of 210 milliliters, which is way too much, right? It's not going to give you the correct concentration. So, very common in sort of dilution problems is you're asked not necessarily how much water that you need to add. So, usually to find the volume of water you would need to add, you take the final volume, which is kind of V2, minus the initial volume, which is V1. So, my final volume was 150 milliliters. My initial there was 60 milliliters that I used, which would tell me that I would need to add 90 milliliters of water. So at this point, after I added my 60 milliliters, I would then put 90 milliliters of water in here. And 90 milliliters and 60 milliliters gives me a grand total of 150 milliliters, which is the total volume that I'm shooting for. At that point, if I gave it a good mixy, shaky, maybe not so much shaky, you will end up with a zero point 0.8 molar solution at that point. So it's very common. Sometimes people will go, oh, I'll just dump 150 milliliters in there. And again, you'll end up with too much volume. And essentially, what you would do at that point is you would make your molarity even smaller because the bottom part here would be even larger than it should be. And obviously, the overall concentration would be too small in that case. Any questions on sort of how to make the solution there? Okay. So why don't you try the next one and see what you come up with here? So 25 milliliters of the 6 molar HCl is diluted with water to hit 115 milliliters. What is the new molarity of the new solution there? Okay, so here again, we're doing a dilution. So we'll do our M1 is our 6 molar. Our V1 is 25 milliliters. M2 is what we're looking for, the new concentration, and V2 is 115 milliliters. At this point, we will solve for M2. So M2 here would be M1 V1 divided by V2. Again, you can convert to liters if you want, or if you're using this sort of formula, you can leave it in milliliters since we have milliliters and molarity. I'm going to try my best here to put everybody in the right spot this time. So we'll go like this, divided by 115. Milliliters should cancel, and we should end up with 1.30 sig fig wise. Everybody's got three significant figures and pretty much everything here. So 3 sig figs there on our answer as well. Any questions on that particular one? Also, it does make sense if we think about it. We did a dilution, so our final concentration is less than where we started. So it went from 6 molar to 1.3 molar. So that does make sense as well. Any questions on dilutions or how to calculate it? Again, on these problems, a lot of times they will ask for how much water you need to add. So make sure you can watch out for those sort of questions. All right, any questions on any of that there? Okay. So why don't you try this last one here, I think. And while you're at it, why don't you also try to figure out the volume of water that's needed to be added? Okay, so same idea. We're doing a dilution. So we'll go with M1 here is 15.9. V1 we're looking for. M2, we're going to make a very diluted solution of 0.05 molar. And our V2 is 200 milliliters. So again, here we could solve for V1 using our M1 V1 equals M2 V2. So V1 M2 V2 M1. And looks like we got 0.05 molar, our 200 milliliters divided by our 15.9 molar. And that will get us 0.05 times 200 divided by 15.9. Looks like something like 0.62, we'll call it 9 milliliters is needed here. Any questions on that there? Let's see here. Now, in terms of sig figs, probably really should come out to here based on this number here, which is 2. So probably should be 0.63 milliliters. So if we were to make the solution, we would take out 0.63 milliliters of our nitric acid. To find the volume of water you would need to add, you would take our final volume, which is 200 milliliters, minus our initial, and we would end up with 200 minus 0.63, something like 199.37 milliliters of water would be needed with it. Again, that plus the 0.63 gives us a total volume of 200 milliliters. Again, given a good mix, you should then have a solution that has a concentration of 0.05. Any questions on that one? Okay. All right, we're going to skip that one, I think. So the next thing we're going to really talk about is stoichiometry. So we've done a number of different sort of stoichiometry type problems. We've done traditional stoichiometry problems where we go grams to moles. We've done stoichiometry problems involving gases, where somewhere along the way that you use the ideal gas law is very common. So here are solutions as well. We could do stoichiometry problems. And really the main difference in terms of solution stoichiometry is really the moles part. So here we use molarity, which is our moles per liter. And very often we use our moles is liters times molarity. So how we get the moles to do our stoichiometry part is really the difference here. Sometimes as well at the end of the calculation, we may actually just figure out the molarity of a solution as well. So those are two sort of common ending sort of problems, is either maybe figuring out how many grams you produce like a normal, or at the end you may actually use the molarity at the end to um, actually calculate the molarity, so the moles and the volume that's given to you. So the basic steps for our solution stoichiometry problems are really the same steps that we've done before. Just like all of it, you want to make sure that you start with a balanced equation. Again, none of it's going to work really well. And really, a lot of times, this is where the difference comes in, is calculating the moles. Again, using that the moles is liters times molarity. If it happens to be a limiting reagent problem, you would need to determine if, the limiting reagent like we've done before. And then the rest of it is mole to mole relationship to get the moles of what you're looking for. And then number 5 here, you could use the molar mass to get the grams. But sometimes even in solution stoichiometries, you will then take the moles to molarity, again, using moles divided by liters. So very common on the back end of the calculation, you'll be asked to calculate something like molarity as well. So let's take a look at sort of how these problems work. And again, the nice thing is sort of the center part or the middle part of the calculation really is very similar to what we've done before. So if we look at this problem here, we're taking 10 milliliters of 0.3 molars sodium phosphate, and we're going to react it with excess lead to nitrate. Assume no volume change. What is the mass of precipitate that is formed? So right off the bat, it tells us that we have excess lead to nitrate. So this tells us it's not a limiting reagent problem, and that this actually is our limiting reagent by default, just based on the information given to us. So we want to start with everything. So step 1 is the balanced equation. So we want sodium phosphate. So that is Na3PO4. Again, you want to make sure that you start with the right formulas. Lead to nitrate is PbNO3 with a 2 on the bottom. This you should hopefully recognize as a double displacement reaction. So our positive and negative guys are basically going to swap partners here. So our sodium will hook up with the nitrate, giving us NaNO3. And our lead will hook up with our phosphate there and make our That is +2, and phosphate, again, to make sure you get the right one, lead is +2 in this case, and phosphate is -3. So common number there is 6. So you would need, let's go underneath, PB3, NO3, 2 in that particular case. And that would be our solid, by the way. Any questions on how to get to that formula there? Also important, right, is we need to make sure it's balanced. So looks like perhaps, let's see here. Oops, that's phosphate. I wrote the wrong thing in there. Let's try that again. We'll go underneath. Let's try PbPO4. There we go. And that's a 2. That's a 3. And that's a 2. There we go. All right. So we have 2 phosphates, so we'll put a 2 there. That gives us 6 sodiums. That gives us 6 nitrates. So a little balancing like that, and that should work, hopefully. Yes. So 2 of the sodium phosphates, 3 of the lead 2 nitrates, 6 of the sodium nitrates, and 1 of the lead 2 phosphate. So we have our equation. It's balanced, which is really our first step. The next thing is to take whatever they gave us and convert them into moles. In this particular case, again, we have volume and molarity. So we can get moles by taking liters times molarity. We want to convert our milliliters into liters. So divide by 1,000 or move it 3 places to the left. We're going to multiply that by the molarity of our sodium phosphate, which would be 0.3 moles per liter. That's going to give us 0.003 moles of sodium phosphate. Any questions on that part so far? Just like a normal stoichiometry problem, we're not interested in our sodium phosphate. We are interested in the solid, which would be this guy. So from the equation, we can see for every 2 moles of sodium phosphate, we get 1 mole of our lead 2 phosphate. I don't know why I keep on writing the other there. There we go. So we're going to use that as our stoichiometry part. So 0.3 moles of sodium phosphate. Using the equation, the mole to mole relationship, we see again 2 moles of the sodium phosphate gives us 1 mole of the lead. We're going to divide it by 2, and that's going to give us 0.0015 moles of our lead 2 phosphate. Lastly, we want, in this case, we are looking for grams, so we want to calculate the molar mass here. Molar mass of lead 2 phosphate is, let's see, lead is, where is that thing? It's 207.2. So 207.2 times 3 for the 3 of them, plus 2 times phosphorus, which is 3097. Plus, in terms of oxygen, I think we got 8 of them, 8 times 16. That gives us something like a molar mass of 811.5 when we do that. So 0.0015 moles of this guy. Using the periodic table, we see we have 811.5 grams per mole. And looks like we end up with something like 1.2 grams of this guy would be produced. So this is sort of a solution stoichiometry problem. It is very similar to the steps that we've done before. Again, this is step one, which is balance equation. This is step two, which is convert to moles. This is step three, which is the mole to mole relationship. And this is step four, which is convert the moles into um, some other unit like grams. This also would represent the theoretical yield, right? So this would be our theoretical yield here of that solid product. Any questions on any of those steps there? So let's take a look at another one here. We want to know how many liters of hydrogen gas is produced at STP if 2.5 grams of zinc is reacted with 25 milliliters of 6.25 molar hydrochloric acid. So why don't you take a minute or two to see what you come up with? Again, start with the equation, figure out, how much you would produce, and then here, STP, probably something to do with a gas. Huh? So somewhere maybe P equals nRT you might need to use. Let's see what you come up with. Okay, so here we have another sort of stoichiometry problem. We're reacting zinc with hydrochloric acid. So we might as well start with the equation or the reaction. So we have zinc plus some HCl. Again, we've seen this reaction before. This is a single replacement reaction. The zinc's going to come in and kick out the hydrogen. The zinc and the chlorine will come together to make zinc chloride, and that is what's going to produce our hydrogen gas that basically gets sort of kicked out in that particular case. We also want to make sure it's balanced, so perhaps a 2 there, and I think that should do it in terms of the balancing part. Any questions on the equation there? So we are given some information about some people here. We have 2.5 grams of zinc given to us. We also have 25 milliliters of this guy that has a molarity of 6.25 molar. So when we look at this, we have information about both of the reactants. And the important part about that information that we have about both of the reactants is we definitely know we could take grams and get to moles. And we also know we could take the liters and the molarity and get to moles, which means we really do have the moles of each of our starting ones. That means that this problem really is a limiting reagent problem because we are given the starting amount of both of those. So you could definitely have a limiting reagent problem that involves solutions, as you see here. You could have one that involves gases. You could have one that mixes everything together as well. So, that's the key thing that you want to remember to look for is if you see you can pretty much get the moles of each of your reactants, then it is a limiting reagent problem. You need to determine it however you want to determine it. So I think in this class, I'm trying to remember, I think we did just two separate calculations to the products to figure out which one produced less. So we'll do it that way here. Again, as we talked about, I think when we did limiting reagent, there's multiple ways you could do it. So in this particular case, we would take our 2.5 grams of zinc. We then would want to convert it into moles using the molar mass from the periodic table. That's going to be 6539 grams per mole of zinc. We're not interested in zinc. We are interested in H2, and it looks like it's a nice relationship here. It's a 1-to-1 relationship from the balance equation. So 1 mole of zinc will produce 1 mole of H2. So using our grams here, we got 2.5 basically divided by 6539 gives us something like 0.0382 moles of H2. Again, using this approach, we do a separate calculation now, figuring out how many moles of H2 will be produced from the HCl. The difference is we're going to use the volume and molarity. We're going to convert our volume into liters, so divide by 1,000 gives us 0.025 liters. We're going to use the molarity of the HCl, which is 6.25 moles per liter. If we do this right at this point, we're now going to be in moles of HCl. We're not interested in the HCl here. We are interested in the H2. So from the equation, we see that 2 moles of HCl will give us 1 mole of H2. So 0.025 times 6.25 divided by 2 gives us, looks like 0.078 moles of H2. Any questions so far on those two calculations? Again, taking this approach, what it will tell us is that this is the smallest, which means that this is our theoretical yield, and also our limiting reagent would be our zinc in this case, right? So we don't really need this calculation. At this point, now that we know that this is our theoretical yield, the 0.0382 moles, if we wanted grams, we could use the molar mass of H2 and figure out grams, but here we actually want the volume. So we're actually going to use PV equals nRT and solve for V, which is nRT over P. Remember that STP means the temperature is 273 Kelvin and the pressure is 1 atmosphere. So putting in our numbers there from our limiting reagent, 0.0382 moles, our R, which is our constant, our temperature, which is 273, and our pressure, which is 1 atmosphere. That gets us 0.0382 times 0.08206 times 273. Gives us something like 0.5, no, try that again, 0.856 liters of H2 should be produced at this particular point. Any questions on that? Could you have solved it another way? You could have. You could have used that relationship that we saw in the gases, that 1 mole is 22.414 liters, and took this number and basically multiplied it by 22.414 liters over a mole. And you pretty much, with rounding, get pretty close to that number as well. So that's an alternative way you could have done it. Again, because this is at STP, and that's where you could kind of use that conversion. Remember that if it's not STP, you cannot use this conversion factor either. Any questions on this one here? So again, you can definitely have a limiting reagent problem involving solutions. You deal with it kind of the same way here that we normally do. Any questions on any of those steps there? Now, a more common sort of solution stoichiometry sort of situation that occurs is basically titrations, which is what the experiment was going to be today and on Wednesday. And in titrations, oftentimes these are acid-base titrations, and usually in a titration, as we will see, we usually use a burette, which is this long glass tube. Kind of looks like that tube that they used in the gas experiment, um, and usually has a flask or a beaker down here. And a lot of times in a titration, you could technically put acid or base up in the burette. So a lot of times we do put the base up there, and you put the acid, say, down here. We oftentimes will use some type of indicator. And basically, we will continue to add, say, base to acid until we hit a point which is known as the equivalence point. And at the equivalence point in an acid base sort of titration, that's the point where all the moles of the acid equals the moles of the base. So that's the exact point where essentially you have added exactly the right amount of base, for example, to completely use up all the acid that was there, say, in the beaker or flask. When that happens, our indicator typically will change color. So it's, for example, phenolphthalein that we will see in the videos is a very common indicator that's used. And it's actually colorless in acidic solution, is colorless in neutral solutions, but it turns a pretty pink sort of color in basic solutions. So typically when we use that indicator, when we hit the equivalence point, we're usually in basic solution, and we will see the solution go from colorless to a pink solution. And what we're looking for is really the lightest color of pink that you could get. And that usually will tell us, and that's why they're called an indicator. It indicates to you that you should stop your titration basically at that point. So it basically tells you when the titration or the reaction is over. And sometimes you'll hear the words endpoint. And endpoint in a titration is basically when you actually stop your titration. So if you do a really good titration, your endpoint and your equivalence point should be very close to each other. Um, and again, we use an indicator to sort of signal to us that it's there. When we do an acid base reaction, especially with a strong acid and a strong base reaction, as we talked about in chapter 7, as it says there, if you get to the net ionic equation, essentially every strong acid and strong base combination will end up with this net ionic equation, which is basically the formation of water. And that's why these guys are oftentimes called neutralization reactions, because basically you make water at the end of it. That's pretty much what's left over. You have a salt as well, but that salt is neutral as well. So it's a very neutral sort of solution at that point. Should actually have a pH of 7-ish at that point. when you hit the equivalence point, and it should be neutral. So we usually use titrations in solution stoichiometry problems basically to figure out things. So in this sort of scenario here, you would, for example, know the molarity of the base, and you would also know the volume that's needed to reach the equivalence point. And down here for the acid, perhaps you just know the volume of the acid. By doing this reaction and doing stoichiometry, we could back calculate, for example, how many moles of base we used and use our mole to mole relationship to figure out how many moles of the acid was there. Once we have the moles of the acid and the volume of the acid we started with, we have everything we need to calculate molarity. So that's a very common sort of process that we use titrations for, is because we know pretty much everything about one of the solutions is a standard solution. We could use that to figure out the molarity of an unknown solution. And that's a very common sort of way that we do it. When we use a burette, by the way, it's kind of like that tube as well, I think, but it does increase as you go down in a burette. So when you're reading it, these are milliliters. You fill it to the top up here, and it obviously comes out the bottom when you use it. So when we end up somewhere in this area, for example, our volume is actually like 1.50 milliliters, not 2 point something. So it actually increases as you go down. Very common, people will sort of misread a burette when they look at it. And to figure out how much we added, it is usually initial final volume minus initial volume on your burette. So you can take where you start and where you end. So that's usually two very important sort of measurements that are made when you're doing a titration. You want to take an initial reading before you start the titration. After the solution basically hits the equivalence point, turns a light pink color, you want a final reading. And the difference between the two is how much sodium hydroxide, for example, or maybe base that you added to that solution. Any questions on that there? All right, so let's take a look at a titration type problem. So for a titration of hydrochloric acid with sodium hydroxide, how many milliliters of sodium hydroxide would be required to react with 1 liter of sulfuric acid? So also important as well is not to use the dilution equation. So very often people will use M1V1 equals M2V2. And sometimes you even see online and stuff, people will sometimes refer to this as the dilution equation. And I'll talk about why you can use that in some cases, but you really shouldn't in titration problems. So I'll tell you why it works in certain cases and not in others in just a second. But let's take a look at the problem really first here. For a titration problem, we have HCl and sodium hydroxide. So we want to start it like a normal stoichiometry problem. We want to take some HCl. It's going to react with sodium hydroxide. We're going to get a salt and water. So if you remember, HCl is an acid, sodium hydroxide is a base. The water is going to come from basically the H from the acid, the OH from the base. So that's going to give us our H2O. And the salt's going to come from the other parts. So that's going to be the sodium and the chloride coming together, giving us sodium chloride in this particular case. It's really a double displacement reaction, right? Positive, negative, positive, negative. So it's the same idea as we talked about, I think, in that chapter. So in this case, let's take a look. I did HCl. That's wrong too. I'm just having a banner day today. Let's just try that again. All right. That would be the right one if we were, Is there two different acids in this? Am I reading this problem right? This seems like a bad problem. Read this one more time. For a titration of HCl with sodium hydroxide, how many milliliters of sodium hydroxide would require to react with that? Yeah. So I think somebody changed this problem, not me. I guess I shouldn't borrow these things. We'll go with H2SO4 here. I think that's what their intention was. So we'll try this again. I'm like, we got too many acids going on in a titration here. All right. All right, so we'll do this acid since it does say sulfuric acid here. So H2SO4 plus our sodium hydroxide Same thing, still the OH and the H from our acid going to make our water. The only difference is here the sodium and the sulfate will come together. So remember, sodium is +1, sulfate is -2. So we want to make sure we get the right formula here. Na2SO4 would be our formula there. Now we also want to make sure to balance it here. So we're going to need a 2 there in front of the sodium hydroxide. And I believe we'll need a 2 there in front of the water as well to balance it. All right, any questions on now I think the correct problem here? All right, now looking at the correct equation here, we see that we're looking for how many milliliters of this guy. And we do know the molarity is 0.625 molar. For our sulfuric acid, we have 1 liter, and it has a concentration of 0.5 molar. So sort of the setup here is we have the sodium hydroxide up in the burette. Down here in our beaker or flask is our 1 liter of 0.5 molar H2SO4. So we're basically going to be adding the sodium hydroxide to the sulfuric acid. Now you may say to yourself, is this a limiting reagent problem? And it's really not, because A, we're looking for the volume of sodium hydroxide. And because we don't have the volume, we cannot get moles of sodium hydroxide. So obviously it's not a limiting reagent problem. So really the only piece of information that will allow us to get to moles is going to come from our sulfuric acid. So that is where we kind of want to go with. If we think about molarity, we have moles per liter. And if we think about the molarity of the sodium hydroxide, we have the molarity given to us. And we have the liters is what we're looking for. So the one thing we're missing is moles. So we could use our stoichiometry to get to moles. So that's why we're trying to get the moles here. So to do that, we're going to start with our moles of H2SO4. Our volume is already in liters, so we'll leave it as 1, times our molarity, which is 0.5 moles per liter. Liters will cancel. That's going to give us 0.5 moles of H2SO4. Now, again, we really want to get to sodium hydroxide. So this is where the stoichiometry comes into play. And what we can see from the equation is for every 1 mole of H2SO4, we get 2 moles of sodium hydroxide. So we're going to use that to get to moles of sodium hydroxide. So 1 mole of H2SO4 gives you 2 moles of sodium hydroxide. And that will get us 1 mole of sodium hydroxide. So what we just figured out now is the moles of sodium hydroxide. So now we have the moles of sodium hydroxide. We have the molarity of sodium hydroxide. We could use that to figure out the liters. So the liters of sodium hydroxide would equal our moles divided by our molarity. Let me see if I got another page. I don't. Now we'll go here. So we'll do it on top here. So my moles, my liters was moles divided by molarity. So what we had for our sodium hydroxide was 1 mole. And our molarity was 0.625. And we're going to put the moles on the bottom so that we end up with molarity, our liters, so the moles will cancel. And we take 1 divided by 0.625 means 1.6 liters of sodium hydroxide was needed in this particular case. So what that means is, in this case, if we started with the titration with 1 liter of the sulfuric acid, in order to get to the equivalence point, we would need to add 1.6 liters of sodium hydroxide until that turns pink. Any questions on that part of the calculation there? So coming back here to this part here, why could you not use this formula here? You can't use this formula here, M1V1 equals M2V2, because it assumes a one-to-one relationship, and it is not a one-to-one relationship. So you will be off if you decided to use the dilution equation, which a lot of people decide to try to use. You will be off because you will not have the right mole to mole relationship. Will it technically work if the relationship between the acid and base is one to one? The answer is yes, it would work. And that's why sometimes you'll see people refer to it as a titration equation, but it's really not the right one to use. You should not use it for it. So you should do the stoichiometry sort of calculation like we did here, and you won't run into any trouble. So just keep the M1V1 equals M2V2 for just regular dilution problems. For titration problems, do a stoichiometry calculation. Any questions on that there? Okay, why don't you, let's do, instead of that next example, let's do one more titration problem. Let's say let's do, what is the molarity of HCl solution if it took, let's go with 155 milliliters of, we'll do magnesium hydroxide to neutralize, we'll do 75 milliliters of the HCl solution. And we'll do a molarity of 0.5 molar. So what is the molarity of the HCl solution if it took 155 milliliters of 0.5 magnesium hydroxide to neutralize 75 milliliters of the HCl solution in a titration? So give it a go. I will as well, since I obviously just made up these numbers. We'll hopefully get the same answer here at the end. Okay, so since we're getting to the end here, let's take a look. So same idea as titration. So really it's a stoichiometry problem. So we want to start with our equation. So it's going to be our hydrochloric acid plus our magnesium hydroxide here, which is going to act as our base. Again, water and a salt. So water coming from the H plus and the OH minus there from the base. That means the magnesium, the chloride will come together, magnesium being +2, Cl being -1, going to give us MgCl2. And at this point, we need to do some balancing. So it looks like perhaps a 2 in front of the HCl would work. And another 2 in front of the water here should get us balanced. Any questions on the equation there? Again, if we just kind of take an inventory of what we're looking for in this really badly written question, and that is molarity here is what we're looking for our HCl. We do know it has 75 milliliters. For our magnesium hydroxide, we know we have 155 milliliters and 0.5 molar. So we want the molarity, which basically means we need moles per liter. So we do have the liters part. So we are looking for moles of HCl, and that's really where the stoichiometry is going to come into play. Here we have volume and molarity, which will allow us to get to moles. So we're going to start with the moles of the magnesium hydroxide, then using the balance equation. That's going to allow us to get to the moles of the HCl, and then we'll have the moles of the HCl in the volume. We could get to the molarity. So that's sort of the pathway we're going to go. We're going to convert our volume into liters, so 0.155 liters times the molarity of our magnesium hydroxide, which is 0.5 moles per liter. That gets us here 0.155 times 0.5, 0.0775 moles of magnesium hydroxide. Again, we need to get to our HCl here. So from the balance equation, we see for every 2 moles of HCl, we need to throw in there 1 mole of our magnesium hydroxide. So we will use that there. 1 mole magnesium hydroxide from the equation gives us 2 moles of HCl. Those are going to cancel. And that will get us looks like 0.155, whoops, 0.0775 times 2, yep, 0.155 moles of HCl. We now have the moles and we do have the volume, so we could take that and divide it by 0.075 liters, which is our 75 milliliters converted into liters. And if we do that, looks like we'll call it 2.07 moles per liter HCl, or 2.07 big M HCl. Any questions on those steps? It really is just a stoichiometry problem. Again, balanced equation, convert to moles, mole to mole relationship, and just something different there at the last step, which is, converting into molarity instead of figuring out grams or volume or something like that. Any questions on any of those steps there? Our solution stoichiometry in general. Okay, so like I said, we're pretty much done with 15. We might talk a little bit about normality. I'm not sure we're going to talk a lot about it. So we'll start probably rolling into 16 on Wednesday. Like I said, we'll move now that we talked about titrations, the titration experiment from today to Wednesday, the one from Wednesday to Monday, exam from Monday to next Monday. Any questions on any of that stuff? All right. Well, thank you for listening to 2 lectures. Have a good rest of your day. Make sure you put here if you haven't done so.